Now that we've introduced the definition of a directional derivative, I'd like to try out a couple problems where we will be finding said directional derivative. We're going to start with the directional derivative of the function f of x is equal to x times y cubed minus x squared at the point 1, 2 in the direction of theta equals pi over 3. So really quickly, just for a little extra visualization, we're going to be at the point 1, 2, and we're going to be creating an angle of pi over 3 with the positive horizontal axis passing through that point. Now, what that means for us is we're going to need a couple of partial derivatives here. Going back to our definition, if we have the directional derivative in the direction of u of f of x naught y naught, this is going to be equal to the partial derivative of f with respect to x times x naught y naught times the cosine of theta plus the partial derivative of f with respect to y evaluated at x naught y naught times the sine of theta. Now we have our theta value. We don't yet have our partial derivatives, but we do know what point we're going to be plugging in, and that'll be 1, 2. So in this case, for our directional derivative of f evaluated at 1, 2, this will be the partial derivative of f with respect to x evaluated at 1, 2 times the cosine of pi over 3 plus partial derivative of f with respect to y evaluated at 1, 2 times the sine of pi over 3. So let's go ahead and evaluate those partial derivatives, and then we'll come back to this definition for the directional derivative. So partial derivative of f with respect to x is going to be equal to, for x times y cubed, we can treat that as a constant times x. That'll leave us with just the constant. For the derivative of x squared with respect to x, that'll be 2x. Evaluating this at the given point of 1, 2, that'll be 2 cubed minus 2 times 1. Simplifying as much as possible gives us 6. Then we'll take the partial derivative of f with respect to y. So heading back to our original function, this time y is the variable, x will be our constant. Here we have a constant times y cubed. That'll be 3y squared times said constant. And the derivative of minus x squared will simply be 0 due to the fact that x was being treated as a constant. So this partial derivative of f with respect to y evaluated at 1, 2, we'll go ahead and plug in x equals 1, y equals 2, and we'll get an answer of 12 here. So next, we now have all of the information to figure out what this directional derivative is going to be equal to. This is going to be equal to the partial derivative of f with respect to x evaluated at 1, 2, that was equal to 6, times the cosine of pi over 3. Cosine of pi over 3 is 1/2. Plus the partial derivative of f with respect to y evaluated at 1, 2, which we got 12, times the sine of pi over 3, which is root 3 over 2. Simplifying each of these, half of 6 is 3, half of 12 is 6, square roots of 3. This would be the value of our directional derivative at the given point in the given direction. And with that in mind, did want to try out one more example. This example can be found on the back of this page. We're going to find the directional derivative of the function g of s and t is equal to s times the square root of t at the point 2, 4 in the direction of 2, negative 1. So to help visualize what's going on here, we have 1, 2, 1, 2, 3, 4. So here is the point 2, 4, and the direction that's been given to us is 2 to the right and 1 down. So this would be the given direction. Rather than defining our angle theta here, or I guess we can define what theta is, but then point out a couple things. We know that this side is 2, we know that this side is negative 1, and if you know the two components and are looking for the magnitude of the vector, we can apply the Pythagorean theorem to get that the hypotenuse is going to be equal to 5, or excuse me, the square root of 5. Now what that tells us is that the cosine of the angle in question is going to be 2 over the square root of 5, and the sine of theta is going to be negative 1 over the square root of 5. That way we don't need to actually find the angle, we already have the sine and the cosine of said angle. Now our directional derivative in this case is going to look like the following. Directional derivative in the direction of u of g, evaluated at the point 2, 4, is going to be equal to the partial derivative of g with respect to s, evaluated at 2, 4, times the cosine of the angle in question, plus the partial derivative of g with respect to t, evaluated at 2, 4, times the sine of the direction. Now the reason that I know it's this order is because that's the same as the order that was given in the problem. S is essentially taking on the role of x, and t is essentially taking on the role of y for what we're doing here. We also retain alphabetical order wherever possible. So with that in mind, we'll need a couple of partial derivatives. Partial derivative of g with respect to s is going to be, what we have here is a constant times s, treating s as the variable and t as the constant. That'll simply be the square root of t. So evaluating this partial derivative at the ordered pair 2, 4, we simply need to plug in t equals 4, and we get 2 for this partial derivative. For the partial derivative of g with respect to t, evaluated at s and t, we can treat the square root of t as though it's t to the 1/2 power and apply the power rule. That'll give us 1 over 2 square roots of t, or simplifying this a bit, s over 2 square roots of t. So when we plug in s equals 2 and t equals 4, we'll have 2 over 2 square roots of 4. Simplifying as much as possible, this will give us 1/2 for that partial derivative. And finally, plugging these in to the given formula will be equal to partial of g with respect to s, that was equal to 2, times the cosine of the angle in question, that'll be 2 over the square root of 5, plus the partial derivative of g with respect to t, which will be 1/2, times the sine of the angle in question, that is negative 1 over the square root of 5. So we're going to wind up with 4 over the square root of 5 minus 1 over 2 square roots of 5. So 4 over the square root of 5 minus 1 over 2 square roots of 5. Getting a common denominator by multiplying the first fraction by 2 over 2. Our numerators will be 8 minus 1. And our denominator will be 2 square roots of 5. That'll be our final answer for this directional derivative.